Hey guys, thanks for coming. My name's Marcello. I'm a medical physics registrar here at Charlie's, and today we're going to be looking at the LINAC. We're just going to look at all different parts that make it up and what each part does. Mostly the beam forming components, and it'll be a pretty quick overview, but hopefully there'll be some valuable information there, and I'll send out the PowerPoint as well so you guys can have all that info ready to go for you. I'm doing this as part of a TEAP competency where you have to provide training and teaching. So yeah, just so you know what the purpose is. And yeah, let's get started. All right, so the aim is to understand what the major components are, how they work, and how they all fit together to produce a beam. So nice and simple. TEAP's made up of competencies. There's 3 levels. Level 1 is the first level. Level 1 is just theory, basically. And so what you're going to learn today is from this competency here. Level 1 for competency 4.1. We're going to cover pretty much all of this, or almost all of this. So this will just give you a taste of the kind of stuff you'll be learning. Most of it you probably covered in your masters, actually. Yeah. So when I did my first Q&A session for TEAP, Monia, sitting there, said, all right, explain to me every component of the LINAC from the PowerPoint to the patient. And I was like, are you serious? There's no way I can remember all that. But it's actually not too bad when you break it down. So hopefully by the end of today, we'll all be able to do that, or at least you take the PowerPoint home and think about it a bit more, and you should be able to do that at the level of TEAP level 1. All right, you guys already done that? So let's just have a quick look at how the LINAC fits together and all the parts super quickly, and then we'll come back and look at each component in more detail. So you've got your AC power supply. That provides power for your pulse modulator, and your pulse modulator provides the big square waves of power for your microwave power source first, and then your electron gun. So that's feeding your square waves, your pulses into your electron gun and your power source, microwave power source. The electron gun, we'll start with the power source first. The microwave power source is feeding microwaves into the transmission waveguide, which then feeds those waves into the accelerating waveguide. And then your electron gun feeds an electron beam in there, and then these waves, operating in line with the structure of the accelerating waveguide, will accelerate that electron beam until it's really close to the speed of light. That electron beam will then be transported through the beam transport system down to the target, and then if you're making a photon beam, the target will produce bremsstrahlend photons. Those bremsstrahlend photons are first collimated by your primary collimator. That beam is forward peaked, so it's going to be flattened by your flattening filter. You also have a dose monitoring system built into the LINAC. That dose monitoring system is going to cut off the beam when your specified amount of monitor units have been reached. Then further collimation is going to happen by your jaws. That gives you a nice square or rectangular field. And then your nice conformal beam, your final level of collimation where you get a nice conformal shape to the beam, is finished off by your MLCs. That's just your central axis, and then finally you have your couch. So if you break it down, it's actually not too complicated. And yeah, something that's not too difficult to remember, and hopefully today we'll all be able to do that. Then you have auxiliary systems as well. So you have your vacuum system that provides a vacuum for these 3 components. You have this gas pressure system that provides an insulating gas for your transmission waveguide, and we'll talk about why that's a gas and not a vacuum later. Then you have your water cooling system that keeps everything nice and cool at a steady temperature. And finally, your focusing and steering coils that steer and focus your electron beam. Some say that's not really an auxiliary system, that's actually just part of the accelerating waveguide. It depends how you think of it. And finally, your circulator that will protect your microwave power source from waves bouncing off this interface here. We'll talk more about that. So that's the basic overview, and now we'll look at each part in a bit more detail. So your power supply provides your your standard 240 volt AC sine wave. That goes into your pulse modulator. So let's take a look at that. So this produces big pulses of electrical power. This is where this really provides the electrical energy that the system needs to produce that beam. These pulses form a square wave. Square waves look like a series of square pulses, pretty straightforward. The height, this is a typical square wave. So I'm not sure if this is a true beam, but it's a typical megavoltage linac. So you can see it's 100 kilovolts. So we've already stepped up from 240 to 100,000. So there's a big step up there. It's also characterized by a width and a period. And then that gives you this quantity called and then from the period you can just invert it and get your frequency. So it's like any other wave in that sense. So these quantities give you another quantity called a duty cycle, and that duty cycle is a nice quantity that characterizes your wave, and it's just the percentage of your period that's taken up by your pulse. So it's just this divide this times 100.25%, and this actually came up in a TEAP exam. So just knowing how the square wave works and these quantities is useful. This is the circuit for the pulse modulator. I just chucked that in for interest's sake. I haven't memorized this or anything. I probably couldn't even tell you how it works, but it's just nice to see that if you're into more electrical engineering side of things. All right, so your pulse modulator is producing these big square waves. Firstly, it feeds those square waves into your microwave power source. This converts these square waves into high-powered microwaves, which are then going to be fed into the accelerating waveguide. So there's two basic types, your klystron, which is used for varion, used in varion linacs, and your magnetron, which is used more so in Electa and the CyberKnife. Okay, let's take a look at the klystron. So you have your square waves coming in, so we're just looking at this interface here. Square wave comes in, goes into a cathode, and then you have a hot wire filament. Does anyone know what happens when you heat up a hot wire? Exactly, yeah. So you got your electrons being produced. Does anyone know what happens when you stick electrons next to a cathode? A negative potential. Exactly, they get propelled. So now you've got these electrons being repelled down the drift tube into electron bunches. Now the bunches come about because of the cavity structure, and I'll show you that a bit later on. This diagram is just a simplified diagram. But yeah, you're basically getting these electrons repelled down the drift tube into bunches, and that's the first input. The second input, it comes from another device called a radiofrequency oscillator. That's usually part of the klystron system. That just produces low power microwaves to go into your drift tube. So you've got these sort of high energy electrons and this very low energy, low amplitude waves, microwaves coming in, and the goal is to really ramp up the amplitude of those waves. So that's how it works. These electrons along the tube will transfer the energy to the wave, and you'll get these nice high power waves coming out. So that's the whole point, just to amplify those waves. Notice the waves aren't being produced, they're being amplified, and that's going to be one key difference between this and the magnetron. Then the electron beam is caught at the end, and that's the end of the electrons there. So typical frequency is 2.856 gigahertz. That's the true beam frequency. This is a real klystron from the true beam. You can see you got the 5 cavities there, so it's not just a simple drift tube, but the principle is exactly the same as this. And the 5 cavities is a typical design as well for klystrons. It's just a fun fact I learned. Not sure why it's exactly 5, but they typically have 5. All right, now we can look at the magnetron. This is a basic diagram of the magnetron. It's similar. If you look closely, you'll see there's a cathode here that the square wave is being fed into. Same as here, square wave feeding into the cathode. But then you have this strange kind of structure called the anode, which is the anode, and it has these like cavities. So what happens is the electrons, I'm sure there's probably a filament in there as well producing electrons, just missing on the diagram, but you've got the electrons there, and then you've got the cathode feeding in these pulses, and what happens is the electrons kind of move around in this a strange pattern, and they cause resonance in these cavities, and that produces microwaves. So then the microwaves are taken up by this antenna, and you get your microwaves. So the difference is the magnetron is actually generating the microwaves, whereas the klystron is just amplifying them. It's generated in this oscillator. But it's a similar principle. And just a quick comparison, magnetrons typically are smaller and lighter, so it can be mounted in a gantry. For example, the CyberKnife has magnetron. It's a much smaller and lighter unit, whereas the klystron can produce much higher power. So you can't use a magnetron for high energy linacs. When you get up to, say, 18 MV, you definitely need a klystron. And I was speaking to one senior physicist who said, in his experience, klystrons tend to last a lot longer as well, so more durable. So, all right, so now you've got your nice high-powered 2.856 gigahertz microwaves. They go into the transmission waveguide. So that's our next component. This will, the purpose of this is just to transport them from here into your accelerating waveguide. That's the purpose. They typically have a rectangular cross-section as opposed to the circular cross-section you're going to see in your accelerating waveguide. They're pressurized, so instead of being in a vacuum like the other components, they're pressurized to about 2 atmospheres with an insulating gas called a dielectric. For TrueBeam, it's a sulfur hexafluoride. And the purpose of this is to prevent arcing, which is like a sort of explosion of that electrical energy, and that prevents all the surrounding components, because there's lots of important components that could be damaged if you didn't do that. So that's the purpose of that. Then you've got this thing called a circulator as part of the transmission waveguide. What that does is it protects the klystron or the magnetron from waves that reflect off the interface up here. I don't have the accelerating waveguide here, but basically they bounce off the interface between the transmission waveguide and the accelerating waveguide and come back down, and they're fed into this load instead of reaching the power source and damaging it. That's the TrueBeam transmission waveguide. That's what it looks like. All right, so the pulse modulator first fed the square waves into the power source. Now it's going to feed the same square waves into the electron gun. So we'll take a look at that now. Purpose is to produce an electron beam, pretty straightforward, and then direct that beam into the accelerating waveguide. So you'll see a lot of similar design features between some of these components. So this one's got a filament as well. When you heat up a filament, it produces electrons. It's also got a cathode. When you stick a cathode next to it, it's going to repel them. It's at negative 12 kilovolts, this cathode for TrueBeam. But then these electrons need to be focused. So you've got some focusing electrodes that really focus that electron bunch into a nice narrow beam. And then that's fed into your accelerating waveguide. So pretty straightforward. Notice that there's this little structure here called a grid. Grid. That just, when that's turned on, it just keeps the electrons from going into the accelerating waveguide. So it's just like prevents the, when it's beam on, that grid turns off and then the electrons can go in. It's just kind of like a switch in that sense. This is what it really looks like. You can see close, if you look closely, there's a grid there. You can see that mesh. That's the grid. That's what it looks like. It's called a triode because there's also a version of this called a diode electron gun, and it's without a grid. I'm not sure exactly how that stops. The diode version stops the electrons going in, but that might be a good thing to investigate, actually. Okay, so you've got your electron beam coming out of your electron gun. You've got your high-power microwaves coming through your transmission waveguide, and these are both being fed into your accelerating waveguide. Purpose is to accelerate that electron beam to a very high speed, up close to the speed of light. For example, 6 megavolts is already 0.997 C, so it's like really fast. 18 megavolts would be, obviously even a lot closer to C. So we need, a lot of energy transfer to these electrons in the waveguide. It's a circular metal pipe with washer discs. If you don't put the discs in, if you just have a pipe, the microwaves are travelling too fast, travelling at the speed of light. But by putting the discs in, it creates an electric field pattern. The pattern itself slows down. The waves are still going faster, but the electric field pattern can actually match the speed of the electrons. So it's synchronized with the electron bunches coming through. That's the purpose of the washers. They also just help transmit the microwaves along the guide, transmit that microwave power along the guide. So there's two basic types. You've got your travelling waveguide used for Elector and your standing waveguide used for Varian. Travelling waveguide is pretty straightforward. Waves go in at one end, they come out at the other, and accelerates the electrons in a nice linear pattern, analogous to a surfer. It's just from one end to the other, accelerating them through. Then you've got your standing wave structure, which is a bit different. What happens here is the waves bounce from one end to the other, and a resonance pattern is produced, a standing wave is produced, based on the superposition of those reflecting waves. You guys know what standing waves are. And that produces an electric field pattern like this. So it's not every cavity that's accelerating them, which means we can take some out, these cavities to the side, because they're not all accelerating the electrons. They're just coupling, they're just transmitting the power along, which means we can make it a lot shorter than the travelling waveguide, which is a nice design feature of your standing waveguide. So quick comparison. The standing waveguide is shorter, but the travelling waveguide is a simpler design. And simpler designs are always good when you're using equipment every day and it's breaking down. But typically travelling waveguide is considered older technology. All right, so now you've got your high energy electron beam that's been accelerated to up close to the speed of light, and it's been focused as well. And that goes into your beam transport system. I'm just going to check the time super quick. Okay. So the purpose of the beam transport system is to transport the beam from the accelerating waveguide down to the target. There's three basic types. You've got your 90 degree, your beam transport system with a 90 degree bending magnet. You've got your 270 degree, which is used by Varian. I think this one's used by Philips or Siemens, but I'll double check that, but I'm pretty sure it's Philips. And then your 112.5 slalom, which is used by Elector. If you look at the 90 degree, it separates the electron beam a little bit into its constituent energies. So it's not a nice focused beam like these other two, and that's called achromatic. And that's an advantage of your 270 and your 112.5. You get a narrower electron beam out of those. So if we look at the Varian, the true beam design, just a little bit closer, you can see there's three magnets here. And then there's a electromagnetic coil here as well for steering. And then you've got your energy slit, which gets rid of some of those. So there is still some spread, and just gets rid of some of those energies, those lower energies, I think, that are out to the side. And so it keeps that beam nice and focused and nice and mono-energetic. All right. So then your beam is now steered down, and it's nice and focused, hopefully nice and mono-energetic, and it's going to hit your target. So that's our next component of the target. There's quite a bit of physics in the target, so we'll take a look at that. So for a megavoltage LINAC, we use what's called a thick target, which is about the thickness is about the order of magnitude of the range of the electrons. We also use a nice high atomic number target, typically tungsten. True beam is tungsten, and I'll explain why we use that in a second. What happens is the electrons interact with the target atoms and produce your bremsstrahlend photons. It's because the electrons are deviated, they're decelerated by the nucleus, and then that results in your photon emission. In the target, most electron energy is converted to heat. Now, obviously, we don't want that. We want it to be converted into photons. So we're going to manipulate some design features to get that efficiency up as high as possible and as little heat as possible. So one factor that governs that is this little relationship here, is that the percentage of energy converted to bremsstrahlung is proportional firstly to your energy of your electrons. That's why you need a nice high energy beam. And secondly to your atomic number of the target. The higher the atomic number, the less heat and the more bremsstrahlung you're going to have. So that's one of the reasons why we have a nice high atomic number at target. So this is the angular distribution of the photons as they exit the target. You can see as you increase your energy, it becomes more forward peaked. So that's why for kilovoltage radiotherapy, use a reflection target, which is at 90 degrees. So you've got like your target here, you've got your beam coming here, and then it reflects down. And so your beam, electron beam's going this way, but your clinical photon beam is at 90 degrees. And that's because of this relationship here. Whereas for your megavoltage, which is this LINAC, it's 180 degrees. So it just comes straight through. And that's called a transmission target rather than a reflection target. The beam itself also has an energy distribution. It's not just monoenergetic. It has a distribution that goes from your max energy of your electrons. That's obviously the highest energy photons you're going to get. And then we place a filter as well, which filters out those low energy photons. Does anyone know why we have a filter? Or why we want to get rid of those low energy photons? That's right. Yeah, those low energy photons are going to be depositing a lot of the dose on the skin, but we want to get to those deeper structures. Yeah. We also have characteristic radiation. Does anyone know what that is?
Isn't that when like a photon in like an outer energy level drops down to a very specific energy level at the photon?
That's right. Yeah, high energy electron's going to knock out a nice inner orbital electron, and then your electron's going to come down from a higher one and emit a very specific energy photon. Exactly. However, for this energy range and this target, you're not going to get that many characteristic photons. So for example, if you have Z equals 74 and 100 keV, which is a nice low energy, you can have 80% bremsstrahlung, 20% characteristic, whereas for 6 MeV, which is this type of LINAC, the same target, you're going to have basically 100% bremsstrahlung. So we don't have to worry about characteristic radiation for MV, but for KV we do. So we have specific filters that filter out that for KV, but don't need it for MV. All right, how about the material? So some things we need in the material is we need it to have high Z, which we've already talked about. A high melting point would be ideal. And/or a high thermal conductivity. So they're the things we're looking for. So a couple of candidates are copper and tungsten. I'll just put the info up first. So why do you think we use copper for greater than 15 MeV, but tungsten for less than 15 MeV? That's a bit of a harder question. But looking at these parameters, have a think. It's kind of like a compromise between the two. Yeah.
Because the thermal conductivity is much higher in copper, so at a higher energy you're producing a lot more heat, and so it's just like you just need to get that heat out, basically.
That's one key factor. Yep. Very good. Yep. There's one more piece to that puzzle.
Isn't it like for copper that when you copper as a transition target, the photons go straight through rather than tungsten, which spreads out more?
They might have different scattering capabilities, but I'm not sure if that's the reason. It might be though, but that's not the one I'm thinking of. But I won't rule that out. Notice that I said before you want a nice high Z. So, but also notice that the percentage converted to bremsstrahlung is based on the energy. So now that you've got nice high energy, we don't need high Z anymore. Sorry here. Now that you've got a nice high energy, we don't need a high Z anymore. Do you see that? So we don't need that tungsten high Z. We can have that compromise, that lower Z, but yeah, like, is it Riley? Yep, like Riley said, we've got that nice high thermal conductivity, which will dissipate that heat. And we're not compromising on efficiency because it's high energy. Does that make sense? Yep. Cool. All right, this is what the true beam target looks like. You've got your 6 MV, your 10 MV, and your 15 MV. That's the side-on view. That's just air gap, and that's your tungsten button imprinted in a copper base. That's kind of what it looks like. Yeah. This is your target drive mechanism that goes in. Your beam is bent around your 270, hits that, and then there's your primary collimator, and then straight into your flattening filter. But we'll go into a bit more detail now. So you've got your nice photon beam coming through, but it needs to be collimated. So that's our next component. We've got our primary collimator. It's just a big tungsten block with a conical hole. That's all it is. The purpose of it is to collimate the beam, to define that maximum field size, but also for shielding. That's why it's so thick. So you get a lot of that beam attenuated. Attenuates the primary beam to less than 0.1%. And yeah, sets your maximum field size as well. Next component is your flattening filter. Flattens the beam. A lot of the purposes of these are, you can figure it out from the name of it. So there's your beam is forward peaked. Remember before we have, you have that really forward peaked beam. And then the flattening filter flattens it out. The purpose of that was, it was more useful when we did 3D conformal. There was less modulation, so having that flattened beam gives a nice uniform dose in the patient, but now we can still achieve a uniform dose without a flattened beam, but yeah, we still use it at the moment. So what material? You can't just use tungsten because the Z is too high. What happens is, pair production happens when the Z is too high. Pair production is when your photons interact with the nucleus and spontaneously turn into a positron and an electron. You've probably seen this before. If we're operating here in that megavoltage range and you have Z equals 74, you can see that you're very much in this pair production dominant region. So what's going to happen is these high energy photons are all going to turn into electrons and positrons. So you're going to lose a lot of these, and the beam's going to be too soft, and we're not going to get that nice penetration that we want. And so, yeah, you can't use tungsten. So what do you use? Copper or aluminium, typically. So, yeah, that gives you less attenuation and less softening of the beam. Obviously, high energy has to be a lot bigger. To flatten it out, low energy is a lot smaller. Pretty straightforward. Does anyone know what's different for electron mode? When you want to make an electron beam instead of a photon beam, in the beam head configuration, does anything change? Or obviously it does, but what changes?
You use a scattering foil instead of a flattening filter.
That's right. Yep. Anything else? That's right. Yep. Anything else in the collimation? That's right. Yeah. Oh, this is too easy. This is yeah, exactly. You take out the target and flattening filter. You put in the scattering foil. One thing you might not know is that a lot of model Linux have two scattering foils. Hopefully, I can teach you something in this class. And they're about 10 centimeters apart. And yeah, you put in your applicator instead of your MLCs. Your MLCs come out, applicator comes in. Applicator has 3 levels of collimation, 2 trimmers and an insert tray. That insert tray is only 5 centimeters above the patient. Does anyone know why we have to collimate it right down to the patient, whereas the photons we don't? Anyone know why?
The repulsion of the electrons, so it's spreading out. The electrons on the top, you have more spread by the time you get to the bottom.
That's right, yeah. I'd say probably mostly scatter, but repelling each other as well. Yeah, the electrons, they scatter out a lot, so you have to keep them nice and collimated. Yeah, and they repel each other too. And then your last level of collimation is your insert tray, which is a cutout, uses a cutout. And you can get that nice, we don't have MLCs, so you get a nice conformal beam by putting in either lead or I think Cerabend is used as well. Then you have your dose monitoring system. This is made up of, first thing to note is that LINAC delivers dose in what's called monitor units. Does anyone know the definition of a monitor unit?
1 centigrade per something.
That's right, yeah. On the right track, yeah.
Adding to that, there's also it needs to be, usually you have a reference field size, it's 10 by 10 typically, and
Correct. Yep, that's right. 10 by 10, D max, and 100 SAD for true beam, for example. Typically, when you have isocentric treatments, so like VMAT, IMRT, you're going to have it at D max, 100 SAD, 10 by 10. Yeah, so that's, and 100 centigrade is one monitor unit in that setup. So before each delivery, you type in exactly how many monitor units you want to deliver, and then what the dose monitoring system does is it cuts off the beam when you reach that level. It's made up of two what's called transmission ion chambers, and they're totally independent of each other. They're sealed, and they're not connected to the same. They're two isolated chambers. One thing, you probably do know this, but you might not know exactly how this works. It also monitors the beam intensity, flatness, and symmetry all the time while the beam's on. So it's a feedback system. You've got these two inner electrodes. They monitor the intensity, and then you have the outer electrodes that monitor the flatness and the symmetry. And so it's keeping that beam nice and flat, keeping that intensity constant all the way through by constantly monitoring that. And that's kind of what it looks like for true beam. One thing that always kind of disturbs me a bit is it's just a big chunk of metal in the beam. So, and it's just somehow it's all going to go through nicely. But yeah, it works. So. Next thing is your jaws. They're just 4 tungsten blocks, look like this. 2 upper blocks, 2 lower blocks, your X and your Y blocks. They'll define your square field and your rectangular field. For true beam, it's a maximum of 40 by 40 centimetres, and they can be asymmetric as well. So they don't have to be square, and they can be off to one side. They don't have to be exactly symmetrical about the beam, the central beam axis. Then your MLCs. These are just a set of parallel tungsten leaves that are configured like so. Each leaf is controlled by a separate stepper motor. The true beam has inner leaves that are narrower than the outer leaves. So there's 2 different stepper motors here, one for the inner leaves and one for the outer leaves. Each of these leaves are situated on 2 banks, and each of those banks are situated on its own carriage. So you have bank A, bank B, and the carriage moves in and out, as well as the individual motors move in and out. True beam has 60 pairs, has 40 central pairs, which are 2.5 mils, so they're there to define a very high resolution inner field. And then you have your coarser outer leaves, which are 5 mils, and there's 20 of those, or 20 pairs. The purpose of multi-leaf collimator is to produce nice conformal fields, and which are necessary for 3D CRT, VMAT, and IMRT. So you can see you can get nice conformal shaped fields there. So different manufacturers have different designs for their leaves. Each leaf has a tongue and a groove. So you can notice here on the side, it kind of juts out on one side and then juts in on the other. The jutting out is the tongue, and the jutting in is the groove. Does anyone know why it has that? Is it not just straight down?
Was there like leakage between the leaves?
Exactly, yeah. Yep. Now, based on that design, which one do you think has the most leakage? Second one, okay. Anyone else want to have a go? Brave? You think Electa has the most? Okay. You're right, Electa has the most. Yeah, so that's interesting. I won't say with certainty that that's because of this design, because there's a lot of other factors like the distance where the MLCs. When the MLCs go out, some designs they fan out a little bit, just a bit of a design flaw. So it might not be purely because of this design, but Electa leaves do have the highest inter and intra-leaf leakage. Yeah, and it could be because of that design. That's the time. Finally, we have our couch. So there's your true beam couch. I'm sure you've all seen it. What's cool about the true beam couch, not all true beams, but for we have 2 true beams with this couch. It has 6 degrees of freedom. So what's good about that is when you're doing IGRT, you take an image of the patient, then you register that image to the patient's CT, you can then provide a 6D correction to that patient's position before treatment to get them nice and lined up with their correct setup position, if that makes sense. Yeah, so that's the couch. Your first auxiliary system is your vacuum pumping system, which will produce a vacuum for the electron gun, the accelerating waveguide, and the beam transport system. We don't want any air particles interfering or interacting with those electrons, so we want a nice strong vacuum in there. It's 10 to negative 9 atmospheres. Next is your steering coils and your focusing coils. That's going to help steer that electron beam and focus it down to a really, really small diameter. That's for your accelerating waveguide. And then you have your water cooling system. That's crucial because there's a lot going on here. There's a lot of electrical energy being pumped through this system that's being converted to heat. And so you want to keep that, you want to keep the microwave power source, the waveguide and the target nice and cool. And so that's continuously running through. And then your gas pressure system, which is providing that dielectric gas for your transmission waveguide. So that's it. Thanks, guys. Have another go at the quiz. And yeah, there you go.